let's say that we are, okay, so let me give you the more of the context here. The whole idea with this eigenvalues and eigenvectors is you're going to be trying to solve some sort of system of equations. And I'm going to give you an example of this. This is not going to happen this quarter, but I'm just going to point out next quarter, we're going to try and solve something like the following. Again, this is if you're taking 17C, if you're not still applicable, don't worry about it. Just the motivation is not as important. You're going to try and solve these differential equations. Dx dt equals 5x and dy dt equals maybe 2x minus 3y. Which might seem kind of weird, but it's some sort of system where maybe x is like a population of deer and y is a population of wolves, and the rate of change of the population of deer is 5 times the number of deer, because if you have more deer, you make more deer. And the rate of change of the population of wolves is 2 times the number of deer minus 3 times the number of wolves, because more deer means there's more to eat, but more wolves means there's more wolves to compete with. It's probably not the real system, but point is you might have a system like this. And we're going to rewrite this as a matrix equation. Dx dt, dy dt is our vector, and it's equal to the coefficient matrix 5, 0, 2, -3 times the variable vector xy. These two things I've written, this over here and this over here, those are the same thing. They are written different ways, but they literally represent the same system of equations. So it's good to be able to go back and forth between them. Okay, so great. But then what you're going to do after that is you're going to want to be able to find the eigenvalues and eigenvectors of this 2x2 matrix. So let's start by finding the eigenvalues, which we typically call lambda. So we're always going to do the following. You're going to take the determinant of a minus lambda I and set it equal to 0. Now, you can do a lot of work here, but I'm going to jump to the chase and say, all you really want to do is take the determinant of your matrix A, which is your coefficient matrix, and you're going to subtract lambda from each of the diagonal entries. So you're going to have a 5 minus lambda, a 0, a 2, and a -3 minus lambda. You can show more work if you want to, right? Like we could have written this as the determinant of, oh yeah, there's something else I was going to say too, of 5, 0, 2, -3 minus lambda times the identity matrix, but there's no need to write that. You can skip straight to just subtracting lambda in each of the diagonal spots. All right, now the determinant forever and ever for a 2x2 matrix, it's just the product of these diagonal elements. It's going to be 5 minus lambda times -3 minus lambda minus the product of the off-diagonal elements, which is 0 times 2. And we're going to set that equal to 0. Okay. Don't do more work than you have to do here. 0 times 2 is 0. I shouldn't multiply this out, because all I'm going to do is multiply it out and then try to factor it again. It's already factored for me for this special case. This is a special case, though. We'll talk about why it's a special case in a second here. So this is factored as 5 minus lambda times -3 minus lambda, which you could certainly rewrite in some other way, like lambda minus 5 times lambda plus 3. But I want to point out that my eigenvalues are lambda equal to +5 and, was it -3 or +3? Thanks, yeah. I'm going to say this many times, but I want you to take it to heart. If you have a special 2x2 matrix, we have a 0 right there or a 0 there, either the things I just wrote arrows to are zeros, you don't have to show all this work. Your eigenvalues are always going to be the diagonal entries. It always works that way if you have a 0 here or both. Not every matrix is going to be like that, but some of them will. And so when you see that, you can kind of take this shortcut. You don't have to. You can do it the long way. But I just want to point out there is a shortcut, and your teachers eventually be like, oh yeah, you can just do the shortcut. Like it's fast, it's easy. We found the eigenvalues, now we have to find the eigenvectors. each eigenvalue gets an eigenvector. So let's find them. Let's start with lambda equal to 5. I'm going to show you both ways of doing this. I'll do one way for lambda equals 5. Actually, not for this matrix. For this matrix is kind of special. We'll just do them the same way. So for lambda equal to 5, we want to solve A times the unknown eigenvector equal to lambda times the unknown eigenvector. Right? We don't know what the vector is. I'm going to write this out. My matrix A is 5, 0, 2, -3. And my eigenvector is the thing we're trying to find, which you typically call xy. You might call it v1, v2, or x1, x2, or whatever letters you like to use, but we don't know what they are at the point. Okay, so now, most of the time you can use either row of equations. Sometimes you get forced to use one. So let's see what happens if we use the first row. I'm always going to use the first row unless I have to use the second row. Using the first row, when I say the first row, what I mean is this first row dotted with this column equal to that first row. So 5x plus 0y equals 5x. And this is one of those cases where that isn't helpful at all. Because what does that tell me? It tells me 5x equals 5x, which is true, but doesn't give me a value for x, right? X could literally be anything. It could be 2, it could be 3, it could be 7, it could be 1,000,000. You have all the choices here. So that's not helpful. So if the first equation doesn't help, essentially you're getting 5x equal to 5x, or if you really want to subtract 5x from both sides, 0 equal to 0. Again, true, but not helpful. We use the second row. The second row equation is going to tell me that 2 times x minus 3 times y is equal to 5 times y. And if you have questions, this is a great opportunity to speak up. Say, oh yeah, what are you doing there exactly? I'm happy to clarify. At this stage, we then usually try to, I don't want to say isolate y because that's not really what I do, but I'll point out what I do and then what you could do. So I'm going to isolate y essentially. So I'm going to stop before I get there. So adding 3y to both sides, I get 2x equal to 8y. I really, really want to avoid fractions if I can. So my next step would be to say x equals 4y. And then if you wanted to, really, you could go all the way and say 1/4 x equals y. And here's the part that I think people have the hardest time wrapping their brains around. At this point, you have to make a choice. You have to pick a number for x. There's only one number you're not allowed to, well, I don't want to say that. There's only one combination of numbers you can't pick for x and y. What are we not allowed to pick both x and y equal to? 0. You can't have 0, 0 as your eigenvector. Any other choice is fine. So what do you want to pick for x? I want to pick 4. Because if x is 4, then y gets to be 1. I like my choices to be integers. But there are literally an infinite number of choices. You could pick your eigenvector to be x equal to 4 and y equal to 1. You could pick your eigenvector to be x equal to 1 and y equal to 1/4. You could pick your eigenvector to be, I don't know, x equal to -1,000 and y equal to -250. All those are valid choices because any multiple of an eigenvector is also an eigenvector for the same eigenvalue. Now, I will tell you the standard choice is this first one. The standard choice being the choice where the entries are integers and they're as small as possible. So even though you could pick 8, 2, or 12, 3, or -4, -1, we're going to pick 4, 1 because that's where they're positive and as small as possible. And nice. You don't have to, but it's sometimes nice to kind of make sure that this actually works. If you take this eigenvector and actually go back and throw it into this equation, just as a check, if you take your matrix 5, 0, 2, -3, and multiply it by your eigenvector 4, 1, you end up getting, let's see, 5, 0 times 4, 1 is going to be 20. And 2 -3 times 4, 1 is going to be 8 plus -3, which is 5. And look, as expected, that is exactly equal to 5 times the eigenvector that we started with. 25 is equal to 5 times 4, 1. Again, it's not necessary to check, but it's nice to see that the thing we're doing is getting us what we are trying to get. Okay. Also, one thing I saw, which I just wanted to, oh God, what was the thing Sarah was saying? Oh, I know what it was. So I would encourage all of you to, if you're going to write your vectors like this, to use brackets, not parentheses. And the reason why is if you wrote this like this, it's not wrong. But the issue with this is that if you do take 17C, there is a notation for something that looks like this that is totally different than this, that has a completely different meaning than a vector. So I really want to stress, instead of using tall parentheses to write your vectors, use tall brackets. It's going to be better for you in the long run for taking 17C. So not this for a vector, write that instead. Do it for me, please. Do it for yourself, because it'll help avoid some confusion in the last 2 weeks of 17C if you're taking 17C. For now, it's not like if you're just taking 17B, write whatever you want. Okay, let's find the other eigenvector. So that was the eigenvalue. So I should point out some notation here. So this is the first eigenvalue I looked at. I'm just going to call it lambda 1. And since I got this eigenvector, I'm going to call it V1. You want to give your lambda and your V the same subscript to indicate that they go together. This eigenvector goes with that eigenvalue. Let's find the other eigenvector. So my other eigenvalue was, I remember, -3, I think. Yeah. So lambda 2 was -3. It doesn't matter which order you number them in. Call either one, either thing. And again, we're going to try and solve A times our eigenvector equal to -3 times our eigenvector. My matrix A, I forgot what it was already. 5, 0, 2, -3 times the thing we're trying to find equals -3 times the thing we're trying to find. All right. Again, the same thing we did before. We're just using the row equations. So this row dotted with this column equals the first row. So my first row equation is going to be 5 times x plus 0 times y equal to -3 times x. This one's a little more interesting, I think. So the 0 times y is just 0. I'm not going to write it anymore. And if I bring all the x's to one side, I'm going to get 8x equal to 0, which means that x is equal to what? Right. Okay. If x is 0, what is y not allowed to be? 0. So what could you pick for y? Anything you want, except for 0. Pick anything you want. Pick 1. But really pick anything you want. Pick 1. Because right, let's say you picked 1 and I picked 8 because it's my favorite number. Are those multiples of each other? Could you multiply this vector by something to get that vector? I should say by a scalar to get that vector? Yeah, by 8. So again, if that's an eigenvector, so is any multiple of it. And the real reason here is because these vectors point in the same direction, right? If you draw the first one, 0, 1, okay, well, there's 0, 1. But if you draw the one I picked, which I maybe made too large, it points exactly in the same direction. It's just 0, 8 instead of 0, 1. But the defining feature of the eigenvector is that it points in the same direction as all the other eigenvectors associated with the eigenvalue. So you can pick anything once something is 0, but pick 1 because that's the choice everyone's going to make. Anything more to say about that? No, I don't think so. Are there questions about what we've done so far? Is anyone talking? No, we'll hold off on that for a minute. Let's do like 2 more examples, and then we'll take temperature here. Where'd you go? Examples. Yeah. All right. Cool. So let's look at, say, yeah. So let's look at one that's not as nice, where we don't have a convenient zero. Let's say our system or our matrix A is equal to, sure, -2, 1, 2, -3. All right. I want you all to find the eigenvalues. They should be nice negative integers. I'll start you off. Determinant of A minus lambda I is the determinant of -2 minus lambda, 1, 2, -3 minus lambda. Find that determinant, set it equal to 0. You will have to multiply it out and then rewrite it as a quadratic that you can factor. Give you like, I'll give you 2.5 minutes. I'm not enjoying this Apple Watch update. Bother me. Can't like switch faces, so you have to like hold on to switch Bob. I don't like it. Anyway, that's not math. We're doing math here. You found them in your board, you can start working on finding the eigenvectors. That's why I'm losing my mind. All right, I think it's been about 2.5 minutes. So let's take a look and see what we get. So determinant should always be a real quick calc, at least the first step of taking the determinant should be very quick. It's that times that. So it's -2 minus lambda times -3 minus lambda minus that times that. You're obviously welcome to simplify. Like you don't need to write 1 times 2. You should just write 2. I'm writing 1 times 2 to remind you what we're doing, but you should just write 2. And then we're going to multiply this out. So we're going to get, let's see. So if you once you practice this enough, here's how I'm going to show you how to do it. I know the negative lambda times negative lambda is always going to give me a lambda squared. You're always going to get lambda squared. There's just no ifs, ands, or buts about it. So you're going to get a lambda squared. I'm going to get a +3 lambda plus 2 lambda, which is a +5 lambda. And then I'm going to get a -3 times -2, which is a +6. And then 6 minus 2 is +4. That's the fast way of putting it all together. But if we multiply this out the long way, right, it's going to be 6 a plus 2 lambda, a plus 3 lambda, a plus lambda squared, and a minus 2 equal to 0. And then we're going to rewrite it like that. And then we hope it factors. Sorry, I thought you had a question, Tiffany, but you're just on. I was like, what do you want to? So they're not always going to factor. In fact, again, I know 17C, when you take 17C, a lot of the time you're going to get eigenvalues that are complex, meaning you have imaginary roots. Just prepare yourself for it because it's going to happen. So here our eigenvalues end up being, well, we get lambda plus 1 times lambda plus 4 equal to 0. So we get lambda equal to -1 and lambda equal to -4. Okay, here we're going to talk about the two different ways you can find the eigenvalues. I personally am always a fan of doing it the way I've showed you already, which is where you start with, let's say for lambda equal to -4, we're going to do A times the eigenvector equal to -4 times the eigenvector. And this is the way I like to do it because I feel like it has more of the meaning involved, but I'll talk about the other way in a second. So let's see here. Oh, and let's write it out. You have A times your eigenvector equal to lambda times your eigenvector. Again, let's use the first row. First row is -2, 1 dotted with xy. It's -2 times x plus 1 times y. And what should that be equal to? -4, -4x, or -4y? I know you know. I know nobody ever wants to say anything. It's okay. Fine. -4x. Drag it out of me. But why is it -4x? Because it's the top row. Right? We're saying the first row, when you do this multiplication, you're actually going to get -2 times x plus 1 times y. And the second row is going to be 2 times x minus 3 times y. And it's going to equal the first row here, which is -4 times x, and the second row here, -4 times y. We just don't want to write all that out because we don't need it. Yeah.
For like the A,
Uh-huh.
I thought you had to do -2 minus -4.
Hold on. We'll get there, I promise.
Oh.
We're about to get there, but I'm talking about how there are two different ways of kind of thinking.
Oh,
So the way you're talking about is the other way, which I do like sometimes. So here, if I use this first equation, right, the first row equal to the first row, then I solve for y, and I get y equal to -4 plus 2 is -2x. And the method I've kind of developed for figuring out what my eigenvector is instead of picking x equal to something and finding y, the thing you can always say is that x is going to equal the coefficient of y, and y is going to equal the coefficient of x. That will always work. So my vector here is going to be y equal to -2. I should have said x first. X equal to +1 and y equal to -2. Or you could pick x equal to 1 and then y will equal -2. Same deal. Questions about this before we do the same thing, but the other way. So we're going to do the same eigenvector just to see how you can do it the other way as well. Do I have enough room on this page? No, not really. Okay. So here's the alternative, or I should say, I probably should say my way is probably more the alternative way. Like, it's just the way I like doing it. I think it's better. I think you see things more nicely. But the other way of doing it is also perfectly good. And there is one specific case where I think it's better than my way. So I will show it to you. So the other way to do it is to say, I'm going to solve a minus lambda I times the unknown eigenvector equal to the 0 vector. So what I end up doing is I end up taking so over here, here's a minus lambda I, just so y'all remember, it's -2 minus lambda, 1, 2, and -3 minus lambda. And then for lambda equal to -4, I'm just going to plug that in. So my a minus lambda I, all that's going to be -2 minus -4. Again, you should just write down that it's equal to 2. And then 1, and then 2, and then -3 minus -4. times the unknown eigenvector, still calling it xy, equal to the 0 vector. This will yield the same eigenvector or a multiple of the eigenvector. It's just another way of getting there. So let's look at, well, let's rewrite it so it looks nicer. So it's a +2, 1, and a +2 and -4. Oh, look, the rows are the same or multiples of each other. And that will actually always happen when you do it this way. If you do it this way, after you simplify your first and your second row, your second row will always be a multiple of your first row. It might be the same as your first row, but it'll always be a multiple of it. It could have been 4, 2, it could have been -2, -1, something that's a multiple of your first row. So basically both the equations become the same. The first row equation is 2x plus 1y equals 0. I don't even want to write the second row equation because I've already written it. It's 2x plus 1y equals 0. So then I get y equal to -2x. And again, my vector is going to be x equal to 1. And then y has to be -2 times 1, which is -2. Same eigenvector. So which way do you want to do it? Take your pick. But make a choice. Make a choice and stick with it. So you just do it the same every time. And I should say, if your teacher specifically wants you to do it one of these ways, they shouldn't really, like, it shouldn't really matter which way you do it. But if they specifically are like, yeah, you should do it this way always, then do it that way always. They're both pretty much computationally the same amount of effort. I happen to like doing it the first way better because to me, it showcases the meaning of what an eigenvalue and eigenvector are. So when you take a matrix and multiply it by the eigenvector, you get a multiple of that vector that points in the same direction. It might just be longer or shorter or pointing in the opposite direction. But that's really the only real difference between the two. So let's find the other eigenvector for the other eigenvalue, and then we will move along to one more example where I will point out that doing it the way we just did it is probably better. Such is life. So the other eigenvalue was, I don't remember what it was. Was it -1? Yeah. Okay. Oh, and again, I should have been smarter about this, or not smarter. I should have been more careful. I should label this as lambda1, and this is v1. And then for the other one, lambda2 equal to -1. Let's do it this way. So the thing I like about doing it the way we just did it is if you've already got this matrix written here, something minus lambda, something, something, something minus lambda, it's very easy just to plug in the value you're picking for lambda here. So my A minus lambda I is going to equal -2 minus -1, 1, 2, -3 minus -1. So when I'm trying to solve A minus lambda I times V equal to 0, I'm really trying to solve this matrix. I am going to simplify. -2 plus 1 is -1, 1, 2, and I'm pretty sure it's going to be a -2 over here because the rows should be multiples of each other. Let's check. -3 plus 1 is -2 times my unknown eigenvector equal to my 0 vector. Use either row you like. They're pretty much the same. So using the first row, I get -x plus y equal to 0. So y equals x, and my eigenvector for lambda2 is v2 equal to, what am I going to pick if y equals x? One, right? X equals 1 and y equals 1. 1, 1. There's my eigenvector. Cool. So finding eigenvectors and eigenvalues is not that bad, but you need to practice it so that you're fast at it because it's easy enough and you're going to get asked about it, but it's not that hard to do once you practice it a few times. Let's do one more just to showcase something that is not quite as nice. So let's look at that example. So here's one more 2x2 matrix. That is this. So we're going to find the eigenvalues, same as we always do. Eigenvalues. So we're going to do the determinant. I do think it's worth writing just this notation before you actually write what A minus lambda I is. Just so if you make a mistake, the person grading your work is like, oh yeah, they knew where to start. So a minus lambda I is going to be 0 minus lambda, -2, -1, 3 minus lambda. All right, we're just subtracting lambda on the diagonal. That is the only change you have to make before you take the determinant. And then that's going to equal negative lambda times 3 minus lambda minus -2 times -1, which is supposed to equal 0. That's going to give me lambda squared minus 3 lambda minus 2 equal to 0. And it really looks like it should factor. It really doesn't. It'd be nice if it did. But there's no numbers that multiply to, there's no integers that multiply to -2 and add up to -3. So we can't factor this. Does not factor. So what we do instead is we use the quadratic formula. So my A value is 1, my B value is -3, my C value is -2, just looking at this. And then lambda is going to be -b, so -3, plus or minus the square root of -3 squared, minus 4 times A times C, all over 2 times A. Simplifying the discriminant here at the thing under the square root, we get lambda equal to 3 plus or minus the square root of 9. 4 times 1 times -2 is -8. So 9 minus -8 is 9 plus 8, which is 17. And I can't really do anything else with that. That's as simple as it gets. Bummer. It's fine. The bummer really is when we start finding the eigenvectors, they're going to be kind of gross. So I will tell you, when the eigenvalues are not nice integers or even nice fractions, you probably want to do it the second way, where you, instead of solving a times the vector equals lambda times the vector, it's probably going to be easier to solve a minus lambda I times the vector is equal to 0. So we're going to do it that way and see what happens. So yeah, I think I have enough room here. So there's my a minus lambda I. So let's pick the one that's plus first. So for lambda 1 equal to 3 plus the square root of 17 over 2, we're going to do a minus lambda I times the unknown eigenvector equal to 0. It's going to become, all right, here's my a minus lambda I. I'm just plugging in this lambda right there and right there. So I'm going to get negative 3 plus the square root of 17 over 2, -2, -1, and 3 minus 3 plus the square root of 17 all over 2 times xy equal to 0, 0. And of course, I should have given myself a new page to work with here. All right, you can pick either row you want, and you should look for the one that looks easier. Sometimes it'll be the first row, sometimes it'll be the second one. Here, to me, I don't want to deal with doing 3 minus this, even though it's not that hard to deal with. I would rather just deal with this. So here's what my first row equation is going to give me. I'm going to get that times x plus that times y. So negative 3 plus root 17 over 2 times x minus 2 times y equals 0. Again, I'm going to isolate y. Well, I'm going to isolate -2 times y. So -2 times y equals positive 3 plus root 17 over 2 times x. This is easier than doing it the other way, because the other way you have like something times x plus something times y equal to something times x. And then you have to like group the x's together, but usually one of them is kind of gross, and grouping them together is kind of a terrible process. That's why this is better. So now here's where we're going to use the trick I talked about before. Instead of trying to like pick something for x and solve for y, we know that x is just going to equal the coefficient of y, and y, I should say, doesn't have to, but x can just equal the coefficient of y, and y just gets to be the coefficient of x. It's really kind of nice. So here our eigenvector, well, x gets to be the coefficient of y gets to be the coefficient of x. And if it were me, I might make a slightly different choice to get rid of at least the fractional part I might choose my eigenvector to be twice this. So multiply everything times 2. And you get -2 times 2. And all this times 2 is just 3 plus root 17. Sometimes we make that choice to get rid of the fractional part. But either one is totally valid. So this one or this one for lambda 1 equal to, I forgot what it was, 3 plus root 17 over 2. Any questions before we do the other one? So this is a reminder, right? The reason we get to say that x equals -2 and y equals that is because if x equals -2 and y equals 3 plus root 17 over 2, then you have -2 times 3 plus root 17 over 2 equal to -2 times 3 plus root 17 over 2, right? The same multiplication. So they obviously have to be equal to each other. All right, here's the good news. The work we're about to do, we don't actually have to do it all. I'm still going to show it to you to show you why, but there's actually kind of a silver lining here. This pen seems to be done. Cool. So let's go ahead and look at lambda 2 equal to 3 minus the square root of 17 all over 2. Right? Almost the same, just 3 minus 3 plus. And so now our a minus lambda I times v equal to the 0 vector. I forgot what a was, to be honest. So let's go back and look at what we had here. Sorry, a minus lambda I, great. It's going to be a negative lambda, so negative 3 minus the square root of 17 over 2, and then -2, and then -1, and then 3 minus the square root of 17 over 2. So that's kind of small. Times my eigenvector that I don't know equal to the 0 vector. Okay, so let's again use the first. So I do recommend, if you do both of these, making the same row choice. If you use the first row in the first one, use the first row in the second one. So using the first row, we're going to get -3 minus root 17 over 2 times x minus 2y equal to 0. We're bringing all that over to the other side. -2y equal to positive 3 minus root 17 over 2 times x. So check this out. Here, the eigenvector we could choose would be x equal to -2 again, y equal to 3 minus root 17 over 2. Oh, sorry, that's v2, not v1. Or if you're like me and you want to multiply everything by 2, you could say that our second eigenvector is -4, and then the second part is 3 minus root 17. So here's something that is true. When your eigenvalues are terrible like this, meaning they're irrational, you have to use a quadratic formula and you get something plus or minus some square root. Well, once you find the eigenvector for the first one, it's going to have something somewhere there's going to be a plus or minus your square root. The eigenvector for the other one, you just change the sign of the irrational part. And the only thing that's changed from here to here is that instead of having a plus root 17, we have a minus root 17. Or instead of having a plus root 17 over 2, we have a minus root 17 over 2. Every other part that is not irrational, the -2 here and the 3 over 2 here, has stayed the same.
So I know like how to do it and everything,
Uh-huh.
like why, like, can you tell me like why we do it?
Like why this works?
Or like why we need to, like.
So what I'm actually saying is, what I'm saying really is, I shouldn't have done any of this work here. What I'm really saying is, if you did this part here and got v1 equal to -2, 3 plus root 17 over 2, then you could have skipped all of this and said, great, for lambda 1 equal to 3 plus root 17 over 2, our eigenvalue is -2, 3 plus root 17 over 2. And then for lambda 2, where I'm just changing the sign of the irrational part, I can automatically jump to saying, okay, great, look at that vector there and change the sign of the irrational part or the root part or the radical part. It's going to be 3. Go ahead.
I knew that, but I was like, what does the numbers in the brackets like mean? I'm just saying like overall.
Okay, so the number, so these numbers in the bracket are the eigenvector coordinates. So meaning our eigenvector here, I mean, you could plug this into a calculator and get a decimal approximation. This is going to be -2, and let's see, root 17 is just a little bit bigger than 4 because it's square root of 16 is 4. So let's say it's like 4.1. 3 minus 4.1 is -1.1. -1.1 divided by 2 is -0.55. So this is approximately the eigenvector -2, -0.55. But what is the eigenvector like? What is the right? I think your bigger question is what's the point? Like, why are we finding this thing?
Yeah.
I don't have a good answer for you right now. Are you taking 17C next quarter? Well, then you'll never get to know.
Okay.
You should take 17C and you'll find out. There are lots of things eigenvectors are good for. So I'm not really good at the why most of the time, but I know I've seen research about how like people use eigenvalues and eigenvectors for like facial image recognition, because you're trying to like take this map of this face that you don't recognize and map it onto another face, and we can represent those things as vectors. And the one that is kind of closest to is the one that is how it's going to get recognized. And those things are the eigenvalue vector thing is the one that maps it to that in a way. I don't really know the science, but I've seen like descriptions of it. So that is why you might use something like this. For us, which we might see again, if your professor starts talking about diagonalization or taking a higher power of a 2x2 matrix that's not just the identity matrix, like if someone starts talking about taking the matrix A, if someone gives you, say, the matrix, A equal to 5, 1, 3, 2, and then they ask you, what's A to the 100th power? Tell me, because that's what we're going to use eigenvectors for. I don't want to force you to sit through it if you don't have to know it, because it's kind of tedious, but it's not too terrible once we know how to use the eigenvectors and eigenvalues. So that's what you might use it for in the next week. But you'll definitely use it in 17C, 17C. Okay, last thing, we got 5 minutes still. Yeah. So those are eigenvalues, eigenvectors. You should practice. Make sure you're good at it. Once you're good at it, you're good to go. The other thing I want to point out is for a 3x3 matrix, there is also a nice way of taking the determinant. So for A equal to some 2x2 matrix, 5, 1, 6, 9, the determinant of A is just 5 times 9 minus 1 times 6, which is, 45 minus 6, which is 39. Cool. But for a 3x3 matrix, the process is more complicated. But there's a nice way of doing it, but it does not extend to larger square matrices. So for 4x4 or 5x5, if someone's asking you to do that, it's a whole other conversation. Let's say we have this matrix, B equal to, 3, 1, 0, 2, -4, 1, -1, 5, 7. And I want to find the determinant of B. Here's what we do. You take this matrix. I usually like to write it. No, I just leave it as is. And either to the right of it, write the first 2 rows, first 2 columns again. So this column 3, 2, -1. This column 1, -4, 5. This will also work if you instead write this first 2 rows below the matrix. Either way is fine. People usually write it this way. And then here's what we do. From upper left to lower right, we multiply the things together, meaning I'm going to do 3 times -4 times 7, 1 times -1 times, 1 times 1 times -1, and 0 times 2 times 5. So the determinant of B, and we're not done, but just hold on. The determinant of B is going to equal this part here, which is again 3 times -4 times 7 plus 1 times 1 times -1. Plus, I don't really need to write 0 times 2 times 5 because it's just going to be 0. There you go. Minus the product in the other way, meaning instead of going from upper left to lower right, you're going to go from upper right to lower left. So minus 0 times -4 times -1 3 times 1 times 5, I should say plus 3 times 1 times 5, plus 1 times 2 times 7. This is not the only way to do it, but it is probably the fastest way to do it for a 3 by 3. So then simplifying this, we end up getting, let's see here. 3 times 7 is 21. 21 times 4 is 84. So negative 84. 1 times 1 times negative 1 is minus 1 plus 0. Minus 0 times stuff is 0. 3 times 1 times 5 is 15. 1 times 2 times 7 is 14. So it looks like we got negative 85 minus 29, which I think is negative 114. That is the fastest way to find the determinant of a 3 by 3 matrix. It is definitely not the only way, but it is the fastest way. So you multiply those, this product, add them together, product, subtract them off. That's kind of. Just be careful, make sure you line things up correctly so that you're not multiplying the wrong things together. So, right, it's this diagonal, this diagonal, this diagonal, this diagonal, this diagonal. All right, close enough. We'll call it a day at 2:58 on Friday.